Hi, everybody, and welcome to 10-1, correlation. Key concept. We introduced the linear correlation coefficient R, which is a number that measures how well paired sample data fit a straight line pattern when graphed. We use the sample of paired data, sometimes called bivariate data, to find the value of R, and then we use R to decide whether there is a linear correlation between the two variables. We consider only linear relationships, which means that when graphed in a scatter plot, the points approximate a straight line pattern. Then we discuss methods for conducting a formal hypothesis test that can be used to decide whether there is a linear correlation between all population values for the two variables. What is correlation? A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. A linear correlation exists between these variables when the plotted points of paired data result in a pattern that can be approximated by a straight line. Here's some scatter plots. I know that it doesn't look like a straight line. However, you can see that as X gets bigger, Y is getting bigger. This has a positive correlation, R equals 0.859. The dots are not tight together. Look at this one on the right. Look how much tighter these are. You can see the line easier in a negative direction on the left. And the absolute value of this is larger than the absolute value of this. Distinct straight line or linear pattern. We say there is a positive linear correlation between X and Y, since as X values increase, the corresponding Y values also increase. So you can see that as X gets bigger, the Y's are getting bigger. There is a negative linear correlation between X and Y, since as the X's increase, the Y's decrease. What if I were to start here and go up like this? I'm not saying that is the line, but I'm saying that could be the line. And the same thing is true over here. And maybe I'm starting here and going down like this. And that's my negative correlation. From algebra, when the slope is going up, it's a positive slope. And when the slope is coming down, it's a negative slope. Now, if I look at this, they're just all over the place. I can't tell where a line might be. They're scattered everywhere. Here, R is equal to 0.074, which is very close to zero. No distinct pattern, which suggests there is no correlation between X and Y. Now here, there is a pattern. If you're familiar with a parabola, it actually looks a lot like a parabola. Is a parabola linear? Absolutely not. Our nonlinear relationship R equals 0.330, which is very small because it's not linear. We do have a distinct pattern suggesting there is some correlation between X and Y, but the pattern is not that of a straight line. We've seen positive straight line, negative straight line, nothing. And here we have a pattern, but it is not a straight line. And R is always between -1 and +1. This is very close to +1, and this is very close to -1. The linear correlation coefficient R measures the strength of the linear correlation between the paired quantitative values X and Y. Calculating and interpreting the linear correlation coefficient R. First, we have some requirements. Given any collection of sample paired quantitative data, the linear correlation coefficient R can always be computed. But the following requirements should be satisfied when using the sample paired data to make a conclusion about linear correlation in the corresponding population of paired data. Number one, the sample of paired XY data is a simple random sample of quantitative data. Visual examination of the scatter plot must confirm that all points approximate a straight line pattern. You want to look at the actual scatter plot and see if it looks like it's increasing, it looks like it's decreasing, it has some type of linear pattern. Results can be strongly affected by the presence of outliers. Any outlier must be removed if they are known to be errors. If all our numbers are between 1 and 10, and then we have a number that's 100, that seems like an outlier, and it seems like it might even be an error. The effects of outliers should be considered by calculating with and without the outliers. Requirements 2 and 3 are simplified attempts at checking the formal requirement. The pairs of X and Y must have a bivariate normal distribution. Calculating, interpreting the linear correlation coefficient, rounding the linear correlation coefficient. We're going to round the linear correlation coefficient R to 3 decimal places so that its value can be directly compared to the critical values. My stat lab will tell you how many decimals to round to. Whatever they say overrides anything I say. Calculating and interpreting the linear correlation coefficient R. Using p-value from Technology Meeting StatCrunch to interpret R, we can use the p-value and significant level alpha as follows. The p-value is less than or equal to alpha. It supports the claim of a linear correlation, and if it's greater than alpha, it does not support the claim of a linear correlation. Properties of the linear correlation coefficient R. The value of R is always between -1 and 1 inclusive. If all values of either variable are converted to a different scale, the value of R does not change. If we multiply all the values by 100, it doesn't matter. R doesn't change. The value of R is not affected by the choice of X or Y. R measures the strength of a linear relation. It is not designed to measure the strength of a relationship that is not linear. R is very sensitive to outliers in the sense that a single outlier could dramatically affect its value. What if I have a scatter plot that looks like this? These are all dots. And then I have a dot here. With that dot, I'm going to have to make my line look more like this. It can't follow the trend of those other dots because that top dot is pulling it. If I were to draw the line that connects all the other dots, it would follow that line. Now, the slope of these two lines are different, and my R is going to be different because more of the values are closer to this new line than the old line because I got rid of the outlier. And since the dots are very close to that line, it'll also change the R value. To reiterate, R is very sensitive to outliers. One outlier could dramatically affect the value of R. Be very careful. Finding R using StatCrunch. This will be chocolate, 5, 6, 4, 4, 5, and Nobel, 6, 9, 3, 2, 11. The table lists 5 paired data values. Use technology to find the value of the correlation coefficient R for the data. Go to Stat, Regression, Simple Linear. Make X var1 and Y var2. I care about my slope is either equal to 0, which means R would be equal to 0, which I would have no correlation, or it's not equal to 0, which means I have some correlation. Compute my correlation coefficient, 0.7949366. And we also have this button down here, which shows me the graph of the points that I plotted and the line of best fit, or the regression line. This is comparing how much chocolate people who live in these countries eat compared to how many Nobel Prizes that country has won. I grab all this data, go into stat, regression, simple linear. My X value would be var1, my Y value would be var2. My hypothesis is all the same. I hit compute. This is our scatter plot surrounding this line. And then we go here and we see that R is equal to 0.801 if we look to 3 decimal places for the 23 pairs of data and significance level of 0.05. Is there sufficient evidence to support a claim that there is a linear correlation between chocolate consumption and number of Nobel laureates? Examining the original data, it does not appear they are randomly selected pairs. Because this requirement is not satisfied, the results obtained may not. The scatter plot shows that the third requirement of no outliers is satisfied. These are not really considered outliers. They're just a little bit further outside of our line. The output shows that the p-value is less than 0.0001, which is right here. We do not use the value for the intercept. We only use the value for the slope. That's a small p-value. We can conclude there is sufficient evidence to support the conclusion that for countries, there is a linear correlation between chocolate consumption and number of Nobel laureates. Our interpretation, although we have found a linear correlation, it would be unrealistic to think that eating more chocolate would help win a Nobel Prize. Since the requirement of a simple random sample is not satisfied, the conclusion of a linear correlation is questionable. Even though we use 23 pairs of data from different countries, only a small amount of countries have at least one Nobel laureate. That's why it's not random, because not all countries will have a Nobel laureate. This may cause a sample bias. Countries with Nobel laureates may differ in a non-random way from countries without Nobel laureates. The consumption of chocolate may vary in a non-random way as well. How are we going to compare countries that have no Nobel laureates to how much chocolate they eat? The value of R squared is the proportion of the variation in Y that is explained by the linear relationship between X and Y. Using the 23 pairs of chocolate Nobel data, we get R equals 0.801. What proportion of the variation in numbers of Nobel laureates can be explained by the variation in the consumption of chocolate? When we square it, it's 0.642. What does that mean? We conclude that 0.642, or about 64% of the variation in numbers of Nobel laureates, can be explained by the linear relationship between chocolate consumption and number of Nobel laureates. This other 36% cannot be explained by rates of chocolate consumption. Correlation does not imply causality. If two things are correlated, it does not mean that one causes the other. We noted previously that we should use common sense when interpreting results. Clearly, it would be absurd to think that eating more chocolate would help win a Nobel Prize. Correlation, if something's linearly correlated, it does not mean that it's the cause of it. For example, ice cream sales versus the amount of sunglasses sold. Ice cream sales would be one variable, and sunglasses sold might be another variable. Does that mean that eating more ice cream means you're going to buy more sunglasses? Or does it mean if you buy more sunglasses, you're going to buy more ice cream? That doesn't really make sense. But They may be linearly related because both these things happen when it's very hot and sunny. That may be more the cause than ice cream and sunglasses, or sunglasses and ice cream. Just because two things are correlated does not mean anything about one causing the other. Common errors involving correlation: assuming that correlation implies causality, using data based on averages. We need data because we need to know where the points are. If something is linear, it doesn't tell me if it's going up or down. Ignoring the possibility of a non-linear relationship. That's why it's very important that we look at the graph. If conducting a formal hypothesis test to determine whether there is a significant linear correlation between two variables, use the following null and alternative hypotheses that use rho, Greek letter RHO, to represent the linear correlation coefficient of the population. Our null hypothesis is rho equals 0. There's no correlation. The alternative hypothesis is H1, rho does not equal 0. If it's not equal to 0, we have a possibility of it being correlated. Use the paired Nobel data to conduct a formal hypothesis test of the claim that there is a linear correlation between the two variables. Use a 0.05 significance level with the p-value method of testing hypotheses. Check requirements. The requirements were already addressed. To claim there is a linear correlation is to claim that the population linear correlation coefficient rho is different from 0. We therefore have the following hypothesis. We have our rho equals 0. Remember, our null hypothesis is always the equal 0 one. And for this, we're going to have a two-tail test because we want to know when it's not equal to 0. It could be positive, it could be negative. We already said that it goes from -1 to +1. Here is the output of StatCrunch. And we can see that our p-value is very small. The test statistic of t equals 6.123. To find the degrees of freedom, it's n-2. The test statistic of t equals 6.123 yields a p-value that is less than 0.01. Because the p-value is less than the significance level, we reject the null hypothesis because we see a linear correlation here. We have a decent size R value, so it looks like it's linearly correlated. We conclude that for countries, there is sufficient evidence to support the claim of a linear correlation between chocolate consumption and Nobel laureates. We're not talking about whether or not it's true. We're just looking at the data. And because my p-value is smaller than my significance level, or it is in the rejection area, there is sufficient evidence to reject the null hypothesis. We accept the alternative hypothesis, which is that they are correlated. Thank you for watching.